Hi guys, so hope you're all well. I'm recording this a day before the paper 3 2020 exam. So if you're an edXL or AQA student, you've got some statistics to do in your paper 3 exams. Hopefully the revision's going well. So this video today is going to be a question that I've come up with, and it's quite a tricky question. I thought this would be a good idea to go for a question which kind of involves a mixture of lots of different things. So we got some hypothesis testing, we got some normal distribution, we got some binomial distribution. So we got a real mixture of stuff in this question, and I thought this would be a nice one to go through. And I came up with this one myself. So let's go through this. We got the heights of year 13 students in a school, and we're going to model it as a normal distribution. So let's just underline the key words here. So we're going to model the heights in the school as a normal distribution and a mean of 165. Okay, so we've got 120 students in year 13 in the school, and we know that 18 of these students have a height greater than 180 centimeters. So let's think about that. We've got reading this sentence here, we've got 120 students in year 13, and 18 of these 120 students have a height greater than 180. So we've got this normal distribution X. Let's just make a note of this here. So actually, I'm going to be really specific about this. So X is the height. X is the height of a randomly. It's going to be the height of a randomly chosen year 13 student. And X has this normal distribution. So it's got a normal distribution with a mean of 165. And do we know about the sigma? So no, we don't know the sigma. So I'm not giving the sigma in this question. So we've got this second paragraph here we've got 18 students with a height greater than 180 centimeters. All of the students with heights between 155 and 170 are asked to complete a survey, and we are going to randomly select a student out of these surveyed students with heights between 150 and 170. So yeah, we don't know the sigma, so I'm just going to put like sigma squared as our variance there. So part A of the question says, calculate the probability that we select a student with a height less than 159.9 centimeters to two significant figures. And I should have actually worded this question a better question. So actually, no, sorry, I know, no, it's fine. Don't worry about that. Right. So yeah, the question says here we're going to randomly select one of these students who have a height between 150 and 170. So what is this part A of the question asking us for? So it's basically saying, given that we select someone with a height between 155 and 170, what is the probability that we select someone with a height less than 159? Sorry, 159.9 centimeters. So this is actually kind of like a conditional probability question. So let's make a note of this here. So this is basically asking us, what is the probability that we select someone who has a height less than 159.9? Okay, so again, read the question. Calculate the probability that we select a student with a height less than 159.9 centimeters. But key sentence before that is this: we are going to randomly select a student out of the surveyed students. Who are the surveyed students? So the surveyed students are students who have a height between 155 and 170. So what is the probability that we select someone with a height less than 159.9 centimeters, given that they have a height between 155 and 170? So this is kind of like a conditional probability question. Now, I know that I've not written all this on one line, so let me try and write it all on one line just to be really clear for you guys. So that is the probability we want to calculate. Probability we select someone with a height less than 159.9, given that we select someone with a height between 155 and 170 centimeters. So that's kind of what this question is wanting us to calculate. That's what we need to calculate. Now, the problem is we don't know the sigma for this X distribution. So we don't know the sigma value for our distribution. Let me just try and make this a little bit smaller so this all fits in nicely down there. So that's what we're trying to calculate. And I'll just write this out here. Okay, so we don't know the sigma, so we're going to have to work out the sigma for this distribution. And this is where the second paragraph comes in handy. So there are 120 students in year 13 in the school, and 18 of these students have a height greater than 180 centimeters. So I'm actually just going to go to the whiteboard. And again, we're just going to copy out the information that I wrote down here on the whiteboard again. Sorry, 1 second. Here we go. So we know that we've got this, so answering part A to the question, we've got this normal distribution with a mean of 165 and an unknown sigma squared, an unknown sigma. And we know, so again, if we just go back to the Word document, so remember that we've got, as the question says here, we've got 18 students who have a height greater than 180 out of 120. So we've got 120 students in year 13, but 18 have a height greater than 180 centimeters. So what that means then is that the probability that we select someone with a height bigger than 180 centimeters is going to be the 15 students in the year group who have a height greater than 180 centimeters out of the total number of students, 120. So again, just to go back to the question, remember we got 120 students in total, 18 have a height bigger than 180. So the probability that you select someone in this year group with a height bigger than 180 centimeters is 18, so this 18 out of 120, the total number of students. Okay, so let's go back to our working. So it's 15 out of 120, that probability. And if we just put that into the calculator, does that simplify to a nice number? Yes, it does. So when we do that, actually, wait, was it, sorry, was my number 15? Was it 18? Sorry, I've made a mistake here, haven't I? Sorry, sorry, not 15 out of 120, 18, sorry, my bad. It should be 18. Sorry, this number there is 18, not 15. Sorry, forget that, that's 18. So we've got 18 students in the year group who are taller than 180 centimeters out of a total number of students in our year group of 120. So if we put that in the calculator, 18 out of 120, we get 0.15. So a 15% chance you select someone with a height bigger than 180 centimeters in this year group. Now we're assuming that we got a normal distribution. So now what we can do, because we don't know the sigma, we can't answer part A of the question unless we know the sigma. We can't answer this conditional probability question. So let's go back to the question. Remember that this part A of the questions asks us to calculate a conditional probability, as we said before. I mean, we can't do that unless we know sigma. So if we don't know mu and sigma, remember what we need to do. So let's just make a note of this. If we don't know, so if we've got a normal distribution and we don't know mu or sigma or both, remember we need to use our conversion to a standard normal distribution. So we need to use our standard normal distribution. So we need to use our Z distribution, which is a normal distribution, the mean of 0 in the middle, and a sigma of 1. And remember our key formula to do that. So what was our key formula? It is that Z, so the Z distribution is equal to your normal distribution, take away the mean divided by sigma. So that's like the graph transformation that we need to do to transform. So let me just draw a diagram so you can actually see what I mean. So we've got, in reality, if we think about like a number line, like you got like 0 there, let's say you got 165 there. So we got like this normal distribution of heights. But what we want to do is we want to transform that so that we get a mean of 0 and like a standard deviation of 1. So that's kind of what we're trying to do here. We're trying to transform the real distribution into a Z distribution, because then we can use the inverse normal function on the calculator because we know the mu and sigma for a standard normal distribution. So it just makes life easier with this calculation here. I'll actually just keep, do you know what, I'm going to keep this diagram on the page actually, because I think that's quite a nice diagram to think about. I'll just move this like that there. And I will rub this out there. Okay, right, so now then, so we've got this probability here. Now what we're going to do is we're taking our probability and we're just going to manipulate the inequality inside our probability function. So we're going to do, so we've got an inequality. What you do to one side, you must do to the other side. So x take away mu divided by sigma is bigger than 180 take away mu divided by sigma. And again, this is the same number as this, like this probability is the same as that. We're just doing the same thing to both sides. So the probability is still this 0.15, so 15%. Now, as we can see on the left-hand side of this inequality, this is just Z. So therefore, we know that the probability that Z is greater than 180 take away mu. Now, we know what mu is. Mu is actually 165, because that's the mean of our distribution, 165 divided by sigma. And we can actually just simplify this. We got the probability that Z is greater than 15 over sigma is equal to 0.15. So let's just, so firstly, let me just squish everything upwards like so. Now let's look at our distribution here. So this is, so this, what I'm calling this here, this is our distribution for x here. Okay, so what we've got is you've got x here, which is our curve distribution for x. Now, the probability, actually, no, sorry, let's forget about, sorry, forget what I was going to say there. But I'm going to draw this normal, standard normal red distribution out again. So I'm going to do that down here. So your mean in the middle is 0. Now, this is our, again, this is the curve that represents our Z distribution with a mean of 0 in the middle. Now, we've got the probability that this Z is bigger than 15 over sigma. Again, this sigma that we don't know yet is going to be 15%. So the probability that you pick a number bigger than this 15 over sigma, so 15 over sigma, that's going to be a positive number. Remember, sigma is always positive. The standard deviation is always positive. You can't have a negative standard deviation. So got this positive number here. The probability you pick a number bigger than this number, 15 over sigma, actually, do you know what, let me try and write this again, because this is a sigma. My handwriting's not looking very good here. So that's 15 over sigma, 15 over sigma on the x-axis there. So the probability you pick a number bigger than 15 over sigma is 15%. So the area under the curve here, remember, probabilities are actually just integrals. That's the way that we think about probability in maths. So the area under this curve is 0.15, so 15%. So what we want to do is use our inverse normal function, because remember what the inverse normal function does is it tells us numbers on the x-axis. So we're going to want to use our inverse normal function. So inverse normal. Now, remember, you've got this area like compartment in your inverse normal function on the calculator. Remember, we said this a few times before in recent videos, your area is programmed in your calculator to be on the left side of your distribution. So you're not going to put in 0.15 as your area. You're going to look at your curve and say, right, so to the left of this number on the x-axis there, what is the area to the left? The area to the left is actually 85%, so 0.85 there. So you're going to put into your calculator an area of 0.85, because remember, your calculator is programmed to take areas to the left of your x value on the x-axis. That's how it works. Now your sigma is going to be the sigma for z, because we're looking at the z distribution. We're focusing on the z distribution. So our sigma is 1, and our mu is going to be the mean of a z distribution, 0. Now we're going to plug those numbers into our calculator, and we're going to see what we get. So go into the statistics menu, inverse normal function. So hopefully you're happy with how you do that. Your area is going to be 0.85. Your sigma is going to be 1, and your mu is going to be 0. We're going to plug that all in, and we get this number. So this value, so I'll just put this here. So result, I'll write the U again because it doesn't look like a U. So result that we get is 1.03. I'll just go to 3 decimal places. So 1.036. So that's our result that we're getting to 3 decimal places. Now, if we just try again to move everything up just to get some more space. Okay, right. So that means that this number on the x-axis, like this number we had on our x-axis over there, is going to be equal to this. Okay, so that means that this 15 over sigma is equal to 1.036. So therefore, that means that sigma is going to be 15 over 1.036. You just put all that in the calculator. So 15, and then you can actually do 15 divided by answer. So 15 divided by ounce, and you get this kind of value here. So you get a value about 14.5 roughly. So we'll just say 14.5 to 3 significant figures. Okay, so that's going to be our sigma. So that's the standard deviation of our distribution. So now we know the sigma. So we know that our distribution is going to be this. We have a normal distribution, and it's going to be a mean of 165 and a variance of 14.5 squared. So that's our distribution now. So now then we can actually go back to the calculation that we actually need to do in the first place. Oh no, sorry, not this page. This is the wrong thing. Sorry, forget this. This here, sorry. Yep. So question A. So again, we're going to survey students who have a height between 155 centimeters and 170. And we're going to randomly select a student out of these students with a height between 155 and 170. What is the probability that out of these students, we select a height less than 159.9 centimeters, two significant figures? So again, this is kind of like a conditional probability question. I'm going to go to the next page to do this. So we need to calculate. So what we need to calculate is this. So need to calculate. So need to calculate the probability that x is less than 159.9. So remember, if we go back to the question, just so we can remind ourselves, we want to find the probability that we select a height less than 159.9, but we're going to select students out of the surveyed students with heights between 155 and 170. So again, that's why this conditional probability. So the probability we select someone with height less than that, given that their height is trapped between 155 and 170. So remember our conditional probability formula. So it's the probability that we select someone with a height less than 159.9, and so intersection or and, you can think about it like and their height is trapped between 155, sorry, that should be a less than sign, between 155 and 170, divided by the probability that their height is between 155 and 170. So that's kind of the calculation that we want to do. Now then, let's think about our numerator of this fraction, because I know this looks quite complicated, especially this numerator here with the intersection. But let's just think about this with a number line. So we're going to draw like a number line down here. We've got 155, let's say, actually, no, let's say the 155 is there. Got 170 there on the number line. And then you've got this 155.9, could be like somewhere there, 155.9 on the number line. So we want to select a height less than, so a height less than 155.9. Sorry, I got the decimal point there. 155.9. So it's got to be less than this height there. Got to be less than that. Okay. And it's got to be also between 155 and 170. So it's got to be between there and there. So where is the intersection between these two straight lines? Well, it's here. Sorry, it's from there to there, isn't it? So these two straight lines intersect in this gap here. So the top probability is actually the probability that x is between 150 and 159. Sorry, 155. Sorry, forget that 0. 155 and 159.9. Hopefully that makes sense. So again, if we think about it logically, we're only allowed to pick people who have heights between 155 and 170. So these are like barriers. You can think about these. This is like a barrier here. We can't select heights below this. We can't select heights above this. So if we want to select someone with a height less than 159.9, well, we've got to select obviously someone with a height between 155 and 155.9. So sorry, 159. Sorry, I've done this wrong again. This should be a 9 down there. Sorry, this is 159.5. Let's be really clear. 159.9. Okay, so we've got to select someone in this intersection gap region between the two horizontal lines. So the probability that we select someone with a height between 155 centimeters and 159.9 centimeters, right? Finally got it right. Okay, and we're going to divide that by this probability here. So I'll just keep the writing in blue just to be consistent. Probability that your height is between 155 and 170. So what we're going to do, so this is now a normal CD calculation. So using your normal CD, so your normal cumulative distribution function, which accumulates areas under this normal distribution. So it's integrating areas under the curve. So we've got this normal distribution with a mean of 165. So to calculate the numerator, so I'm going to call numerator, I'm going to call it num. So num for numerator. To do the numerator, your lower is going to equal 155. Your upper is going to equal 159.9. And your sigma is going to be the sigma that we had before. So this 14.5. So 14.5. And then your mu is going to be the mean, 165. So we're going to plug that into our calculator and we will see what we get. And then our denominator of the fraction is the same, but the only difference now is for the denominator, your lower still the same, but your upper now changes to 170. So upper 170, same sigma 14.5, same mu 165. Now let's see what we get when we calculate our probability. So when I do so normal distribution in sorry, not inverse normal, sorry, just doing this on my calculator. So normal CD, lower 155, your upper is going to be 159.9, sigma is going to be 14.5, mu 165, plug that all in. So our numerator is going to be this, so 0.1173 to I'll do it to 4 significant figures, so I'll just leave it like that. And then we're going to divide it by our denominator. So the only thing that changes is just the upper value. So that changes to 170. Plug that all in, and we get 0.3897. I'll round that up to 4 significant figures. So when we do this, we can go to the main run maths menu. So 0.1173 divided by, I'm just going to press shift answer. So I get this. So I get about 0. I mean, you may get slightly different numbers depending on like how accurate your numbers you use are, but it's going to be approximately, I mean, I'm guessing about 0.01 here. I mean, if we read the question that I wrote, if we go back to my question, I say here to leave the answer to 2 significant figures. So actually, we're just going to have 0.3. Oh no, sorry, I've shared the wrong page again. Sorry, 0.3. So this is going to be equal to 0.30 to 2 significant figures. 2 significant figures, 0.30. Okay, so that's part A done. So that's the probability of selecting someone with a height less than 159.9 centimeters out of the surveyed students. So let's go back to the rest of the question. So now then, what happens is that 1 year later, in next year's year 13 students, so obviously, you know, you guys have now left, you've now finished year 13. Next year's year 13 students are going to come and do the survey. So they're going to go through the same process as above. So you've got your new year 13 students, and again, we're going to select everyone between 155 centimeters and 170 centimeters, and all those people are going to do a survey. Okay, so we're going to assume that next year's year 13 students follow the same distribution as you guys. So it's the same distribution as before is what we're going to assume. And now what we've got is we've got this suspicion that the probability that we got in part A is actually different for these new year 13s. Okay, so these new students, next year students, we've got a suspicion that this part A probability, this conditional probability, is now different. So out of the students in next year's year 13 with a height between 155 and 170, so out of all these guys in next year's year 13, who have a height between 155 centimeters and 170 centimeters, we're going to take a sample of 20 of these guys, and what we get from our data is we're going to measure their heights, and we find out that 3 of them have a height less than 150. Again, sorry, this should be 159 there. So I've made a mistake there. Forget that. This is 159.9. So we've got 3 of these guys out of our 20 in our sample have a height less than 159.9. So we want to do a hypothesis test at the 5% significance level to test the suspicion of the score. So again, what we want to test is we want to test whether the probability we got in part A is now different. So again, the key word here, different. So we're testing whether the probability has changed. So this is not a one-tail test. We're not saying, oh, has the probability decreased or has it increased? We're saying, okay, is the probability different? So this is going to be a 2-tail test. Let's just make a clear note of this. So this is now a 2-tailed test. Has the probability changed? So one thing to be aware of with this, so I know that in part A we were doing like a normal distribution question. Obviously, you know, we were doing a normal distribution calculation. In this part B, is this hypothesis test going to be a normal distribution hypothesis test, or is this something else? So let's again read the question. We're going to test whether this suspicion is true. whether the probability has changed. And then what do we do in our experiment? So we don't measure people's heights. So we're not, measuring all these students' heights, thinking, oh, let's measure their heights. We're taking a sample of 20 and we're counting the number of them that have a height less than 159. So we're not when we're doing this, collecting this data, we're not gonna, well, I mean, we are kind of measuring their heights, but we're not recording their heights. We're not taking like the mean of their heights. Okay, we're not taking the average. We're not using that continuous data. We're just counting. We're counting how many of these students have a height less than 159.9 centimeters. We're counting. So we're not using a continuous distribution. We're counting the number of successes that we get out of a sample of 20. What is this going to be? This is going to be a binomial distribution hypothesis test, because we're counting discrete numbers. We're counting the number of students who have a height less than 159.9 centimeters. This is continuous data. Obviously, yeah, heights. Heights. Let me repeat that. Forget what I just said there. This is discrete data. Heights, of course, continuous, but we're not worried about the average height. We're not, taking the mean of their heights and doing like a normal distribution test. We're just counting in our sample 20, how many of these students have a height less than 159.9 centimeters? We want 3 successes out of 20. We're talking about a binomial distribution. So let's call, I used X, the letter X in part A. So I'm going to use a different letter now. I'm going to use Y. So Y is going to be, so assuming the previous year was true, the previous year's distribution is, sorry, let me say that again. Assuming the previous year's distribution is the same as next year's distribution, then what we've got here is you've got the Y is a binomial distribution, so binomial. And what's our end value going to be? So we've got a sample of 20 students, and we've got a probability success. So what's the probability? So again, we're going to pick same process before. We got this survey, and only heights between 155 and 170 are allowed. What's the probability of success of picking someone with a height less than 159.9 centimeters? It's what we calculated before, wasn't it? So it was this part A answer. So this answer, part A, was 0.30. So that's going to be our probability of success there, 0.30. So we got this binomial distribution, 20 trials, 20 people in our sample, and the probability, assuming that, last year's distribution is the same as the new year's distribution, the probability of our, quote, success is 0.3. Okay, so now then what we're going to do is a binomial distribution hypothesis test for this data here. Let's go back to the whiteboard so we've got some more space to do some working out. Okay, let's go to a new page. So part B, so my answer to part B. So what we've got is we've got Y, so let's call Y. So Y is going to be the number, so number of students in the sample of 20. So in the sample of 20 with a height less than what was again 159.9, wasn't it? 159.9, sorry, 9 centimeters. So again, assuming the previous year's distribution is true, Y is a binomial distribution, so binomial with trials of 20 and probability success 0.30. So 0.3 basically. Okay, so now let's write down our hypotheses, because obviously we're doing a hypothesis test. So what is our null hypothesis? So what's like the status quo assumption? So again, we assume, to do the calculation that we're going to do, we're going to assume that the probability was 0.30. So our probability that we had before. So the probability of selecting someone with this height less than 159.9 centimeters, 0.3. And what's our alternative hypothesis? So again, let's go back to our question and let's interpret the question. So again, there is a suspicion that the probability is now different from the previous year's probability. So therefore, sorry, I've shared the wrong page again, right? Whiteboard, that's what we want. So probability is not equal to 0.30. So again, we're doing a two-tailed hypothesis test. So we're doing a two-tailed hypothesis test. And it's a 5% significance level. So just make a note of this here, so it's a 5% significance level. So remember what this significance level means. So it's something that as a statistician we decide. So we're going to decide that we're going to do a test at a 5% significance level, which means that we got a 5% chance we're going to say, right, as statisticians, we're going to collect the data and we got a 5% chance of rejecting this null hypothesis. So we're going to assume, right, so we're going to collect the data and we've got to assume that the probability of getting someone with a height less than this is 30%. We've got to assume that. But what we're saying is, okay, so there's a 5% chance that actually this conclusion or this assumption, I should say, so there's a 5% chance that this assumption is actually not going to be true. Well, sorry, let me rephrase that. So there's a 5% chance of rejecting that assumption. So we're gonna specify, we're gonna collect the data, and we're gonna say to ourselves, right, let's give this test a 5% chance of rejecting this assumption. Okay, so now let's think about this. We've got a two-tailed test, and it's a 5% significance level. So remember what we have to do as statisticians. We've got to split that significance level in half. So we've got obviously discrete data, binomial discrete data. Let's try and draw like a number line to kind of like see what we've got going on here. Actually, let me do a bigger number line down here. Right. Actually, no, I'm going to draw the line as down as possible. So you got 0, 1, 2. So like this x-axis here is the number of people with a height less than 159 centimeters. Sorry, 159.9. So number of people. I'll just say number of people for simplicity. Of people. So you got 20 people in a sample. So you could get 0 successes. Obviously, you know, you could collect your 20 pieces of data, and no one could have a height less than 159.9. So that's 0 successes. You could get 1 success, 2 success, 3 success, 4, 5. To be honest with you, I can't be bothered to write the rest of these, but you know, we're going up to 17, 18, 19, and 20. So basically what we've got is we could have like a y-axis like this, and our y-axis is probability. So remember, we're dealing with discrete data, so all these whole numbers here on the x-axis, and this graph is going to be like a line chart of probability. So you could have something that looks like this. Maybe you've got probability. So this binomial distribution may look like this. I mean, it's not accurate, but let's just say it looks something like this. These are all the probabilities here, probabilities. So this is like a line chart with all our probabilities, and our height is the probability of getting this number of successes. So number of people or number of successes is our x-axis. The probability of getting that number of successes is our y-axis. So if we're doing a two-tailed test, 5% significance level, remember what this is meaning. So it's meaning we're going to split that 5% probability, that 5% chance of rejecting this notion that the probability of success is 0.3. We're going to split that into half. So remember, we're going to split that into half. So we're going to have 2.5% on the lower side of the distribution. Let's just write this down here. So we've got 2.5% chance of rejecting H0 for big values. So for big values, so for big numbers of successes. And we've got down here a 2.5% chance, 2.5% chance of rejecting H0 for small values, so like 0, 1, those kind of small values. So that's how our distribution works. So again, the key thing here is that we're splitting that significance level in half. 2.5% is dedicated, so that 2.5% chance is dedicated to tiny numbers in the distribution, and that 2.5% on the other side is dedicated to the big extreme numbers on the other side of the distribution. Okay, so then now what we've got, so if we go back to the question and actually read what we got when we collected the data, we've got our sample 20 and we collected the data, and 3 of them have this height less than 159.9 centimeters. So 3 out of 20. So again, let's go back to the whiteboard. So when we collected the data, we got 3 successes out of 20. Okay, so 3 successes out of 20. Let's just move this up a little bit. So from data, we got 3 successes out. Sorry, let me write that again. So 3 successes out of 20. Okay, so what we want to do is we want to test, okay, well, we're going to assume that the probability of success is 0.3. So we're going to assume our H0, that there is a 30% chance of success. We collected the data and we found from our experiment that 3 people had a height less than 159.9 centimeters. What we want to do is you want to work out how likely that is. If our probability of success really is 30%, how likely is it that we get 3 successes out of 20? So the key thing to bear in mind now is that, so this seems a little bit counterintuitive, and this is what some students get confused with, and what I used to get confused with as well. We don't want to work out the probability that this y distribution equals 3. We want to calculate the probability that y is less than or equal to 3. So why do we want to do that? So we want to calculate this probability because remember, we've got this 5% chance of rejecting the null hypothesis. We're dedicating half of that chance to small numbers of successes and half of that chance to big numbers of successes. So the key thing to bear in mind with this kind of two-tailed significance level test is that if we've got a critical value, so let's say we've got this critical value in the lower side. So I'm going to call my lower critical value, so my lower end critical value, so my lower end CV. And when I say lower end, I'm talking about the small numbers of successes that we could have. So our lower end critical value, let's call that, I'll call that L. Actually, I'll call it capital L just to make it look nicer. Capital L. So we've got this critical value here, capital L. So it could be 0, could be 1, could be 2. So it's the biggest number on our number line such that we reject H0 in the lower side of our distribution. So what we're saying is we're saying the probability of rejecting H0 in the lower side of our distribution with these small numbers has got to be 5%, so 0.05. So the reason why we want to calculate the probability that y, this distribution we got here, is less than or equal to the number of successes we got from our data, 3, is because basically if this probability is bigger than 5, sorry, this is wrong here, this should be 0, let me rub this out, sorry, forget this, 0.025, because remember, we're splitting 5% in half. We've got a lower end significance level, and we've got an upper end significance level. So if this probability of getting 3 successes or less is a bigger number than 2.5%, then it means the probability is too big to reject H0. So it's too likely to get 3 or less successes. So therefore, we can't reject this probability. We have to accept this probability because the chance of getting 3 successes is bigger than the significance level. Now, if our probability of getting 3 or less successes is smaller than this significance level, so if it's really, really tiny, so if the chance of getting 3 successes or less is so small that, you know, it's smaller than the significance level that we decided, then it means it's really, really unlikely that we get 3 or less successes. So it's therefore really unlikely that the probability of success was actually 0.3 in the first place. Do you see what I mean? So we've got to calculate this probability and compare it with our significance level probability. Okay, so let's do that. So the way that we're going to do this, we want to calculate this probability. So what we're going to do is we're going to just use the calculator. So we're going to go to binomial CD on the calculator, because remember, binomial CD, binomial cumulative distribution. So we're accumulating these probabilities, we're adding up these probabilities. So we're going to go to binomial CD on the calculator. The x value is the maximum number of successes. So the maximum number of successes for this probability is 3. So x is 3. Number of trials is 20. And your probability of success, assuming H0, so remember, we've got to assume H0 with this calculation. Otherwise, we can't do a test in the first place. We assume that the probability is going to be 0.3. Sorry, 0.03. Let's go to our stat menu, binomial distribution, binomial CD. So our x, number of successes 3, number of trials 20, probability of success 0.3, execute all that. So what do we get? So we get a probability equal to, so this probability here, let me just write the equal sign there. So when we calculate using this, these data here and using this here, we get a probability of success of 0.107. It's about roughly 10%. So we've got a 10% chance of getting 3 or less successes. Now, this probability is bigger than the critical value probability here. So the probability of rejecting H0 for low numbers of successes. So this is bigger than 0.025. So what is that telling us? So it's telling us that the probability that we get 3 or less successes is bigger than the lower side, the lower end significance level. So it's quite a big probability. So that's telling us that basically, because it's quite a big probability, we should not reject this probability, this initial probability of success. So it's telling us that we've got a 10% chance of rejecting, so we got a 10% chance of getting 3 or less successes out of 20, assuming this is actually the number, this is actually the probability of success. So it's actually, we should not reject that probability. So we have to accept that actually this could be the probability, because basically this chance here is too big to reject that notion. So therefore, what we've got to do is you've got to accept H0. So you've got to accept H0. So there's insufficient evidence. So insufficient evidence to suggest that the probability has changed. So insufficient evidence to suggest that probability has changed. So the probability of picking someone with a height less than 159.9 centimeters changed. So I'll just put this in brackets. Probability has changed of picking someone out of the surveyed people with height less than 159.9. If I can fit that in, let me just I have to move my writing because my one of my tools is in the way. Right here, 159.9 centimeters. Okay, so that'd be our conclusion. So we call this method here a p-value test. Now, you may have been taught another method in school, so I'll just put this here, that this method number 1 is a p-value test where we work out a probability value. So you may have been taught a different method, and I'm going to go through that as well, because obviously I want to make sure that you guys, you know, different people have different ways of doing these kind of tests, and there's 2 methods that we can use. We can either calculate a probability value, which is what we did there, or we can do the second method, which you may prefer, of doing a critical value test. So a critical value test, which is where we find the critical value, or we find the critical region, and then we work out is 3 successes in our critical region. So this is method number 2. So, okay, so to do this critical value test, what we're going to do is we're going to have to use our tables. So remember again that we've got a 2.5% chance, so 2.5% chance of rejecting H0 in lower tail of distribution. So for tiny numbers of successes, so in lower tail, and we got a 2.5% chance of rejecting H0 in upper tail. Okay, so now then, what we can do is go to our tables. Now, I'm actually aware that AQA students, if you're an AQA student watching this, I'm actually aware that you aren't given tables. I think one of my AQA students said that you aren't given tables. So just bear with me for a minute. So EdXL students, you are given tables. So what you can do is you can now use your tables to find where this critical value is. So that's what we're going to do now. Now, remember, because we got 3 successes, which is in the lower side of our distribution, so we can, let me just actually do this first of all. So we've got this binomial distribution again. Sorry, this is Y, isn't it? I've called this distribution Y. With 20 trials, 0.3 successes. So remember that the mean of a binomial distribution, so the mean of the binomial distribution, this Y distribution, is n times p, is 20 times 0.3. Do that on a calculator, 20 times 0.3, you get 6. So yeah, I mean, because we got 3 successes, which is less than the mean of this distribution, we're only worried really about the lower end of the distribution, which is why we picked the less than sign there. That's why we're looking at the lower end of our distribution rather than the upper end of our distribution. Now, so what we're going to do, so we've got this 2.5% chance of rejecting H on the lower tail. We're only interested again in the lower tail of the distribution because we only got 3 successes, which is in the lower tail of the distribution because it's less than the mean. So if you get a number of successes less than the mean, focus on your lower tail. If you get a number of successes bigger than the mean, then instead you actually want to focus on the upper tail. So 6 would be there. So this is kind of like our upper tail. So that's going to be our upper tail there. So I call this UT for upper tail. And everything down here is our lower tail. So we're only really worried about our lower tail. So I'll just make a note of this here. So we're going to focus just on our lower tail. Okay, so we're going to go to our tables. Now, I've got this up on one of my tabs, this tab here. Right, let me share my screen with you. So this is the Edexcel formula book with all your stats tables. Again, if you're AQA, just bear with me. I will go through this if you're an AQA student. Now, you're going to go down to your stats, your stat distributions, and you're going to go down to, there we go, your statistical tables. Now, what is our end value for this distribution? What's our number of trials? It's 20. So we're going to go down to n equals 20. And what's our probability of success? So it was 0.3. So this 0.3 there. So I'm going to go from 0.3. So again, assuming H0, that's your probability of success, 0.3. So I'm going to go down to 0.3. I'm going to go down to 20, n equals 20. And how many successes do we get? So X is our number of successes, 3. Now, because, right, let me just follow this down here. So 0.3 is 5 along from the right-hand side. So down in this part here. So that part there. So it's, so we want 3 successes. So it's in this column here, 3 successes, 0. Yeah, so as we got here, actually from the calculator, 0.107. So actually what you can say is you can actually just read your tables there and you can say, well, okay, so instead of using like the normal CD function, what you can say is, okay, well, the probability that you get 3 or less successes is 10.7%, 0.107. So again, that's bigger than 2.5%. So we got to accept H0, so we can't reject it. So if we go a little bit further down to 2, so the probability you get 2 or less successes is 0.0355. So again, that's actually still bigger than 2.5%, isn't it? So that probability there is still bigger than 2.5%. So again, if you got 2 or less successes, you would actually still have to accept H0, because remember, we're dedicating 2.5% of the significance level to the lower tail. So again, the probability you get 2 or less successes from your tables is 0.035. So that's still that's still bigger than 2.5%. But if you get 1 success, so the probability of 1 success, that's 0.0076. So that probability is now less than 2.5%. So the critical value is 1. So the first value in which you now reject H0 is actually X equals 1, so 1 success. So we can see that the critical value is 1 in the lower tail of the distribution. So 0 and 1 are both in the critical region, because if you get 0 successes, again, the chance to get 0 successes is tiny. It's much more smaller than 2.5%. And the chance that you get 1 or less success is 0.0076. So again, remember that these tables here don't tell you the probability of getting X number of successes. Is a cumulative distribution. So these numbers here are accumulated. They're accumulating the probabilities. So this X equals 1 here that I've highlighted, this is the probability that you get 1 or less successes. Okay, so we can see that the critical, so from our tables, if we go back to the whiteboard, so we can say from our tables, so if we're doing this critical region test, so from our tables, we see that the probability of getting, sorry, y, isn't it? I'm not using X, I'm using Y with this question. So the probability that Y is less than 1, again, from our critical tables, if we go back to our tables, the probability that we get 1 success, it was this one here. So 0.0076. Let's go back to our whiteboard. So that's 0.0076. So 0.76%. So again, that's less than, if we just try my best to keep everything on the same page. So that is less than the significance level in the lower tail, so that's less than 2.5%. So therefore, we can say that one success and 0 success is in our critical region. So 0 successes. So I'm actually just going to write it like this. So a set. So 0 and 1 are in the critical region. So remember, the critical region is the set of successes such that you reject H0. So that's in our critical region. Now, therefore, we can see, and actually what I'm going to do as well is do the critical region for the upper side of the distribution. So let's, again, go back to our tables. So for the upper end of the distribution, again, it's this column here that we're looking at. So this, sorry, let me go back down. So this column here, so 0.0008, 0.0076. So again, 2.5% chance in the upper tail of rejecting H0. So if we look at these big numbers here, so we got the probability that you get 10 or less successes is 0.9829. Okay, so I mean, if we go to the calculator and do 1 minus that, so 1, and let me actually just annotate on the screen here so you can see. So we can see from the table there, the probability of getting 10 or less successes is 0.9829. So that means the probability of getting 11 or more successes is going to be 1 minus that, so 1 minus 0.9829. And if we do that on the calculator, we get, so with this, we get 0.0171. So we know that 11 must be in our critical region. So everything bigger than 11 must be in our critical region. So I'm going to call C our critical region. So we know that 0 and 1, that's in our critical region. So these numbers of successes are numbers of successes that, if we got that from our data, if we got those number of successes in our sample of 20, we would have to reject H0. Now let's look at this probability here. So we've done this probability here. So the probability of getting 11 or more successes is 0.0171, which again, let's just be really clear about this. This probability is smaller than our significance level of 2.5% in the upper tail. But let's just check. So let's just work out quickly the probability that X is bigger than 10, bigger than or equal to 10, which is equal to 1 minus the probability that X is less than or equal to 9, which is equal to 1 minus. So the probability that X is less than or equal to 9 is that probability there. So 1 minus 0.9520. We do that on the calculator, 1 minus 0.9520. We would get 0.048. Now that's actually bigger than 2.5%, isn't it? So that's bigger than 2.5%. So 10 is not in our critical region. So our critical region, I know I've made a bit of a mess of this, but I'm just gonna so I'm just gonna rub this out here because hopefully that will make sense. So 10 is not in the critical region because the probability that you get 10 or more successes in the upper tail is too big. It's bigger than 2.5%. I'm just gonna rub this working out here. So basically our critical region, using our tables, our critical region, so the number of successes such that we would reject H0 is 0, so definitely 0, definitely 1, 11, 12, 13, 14, 15, 16, 17, 18, and obviously 19 and 20 as well. Okay, so what we can say then, so using this, we can say that the critical region, so yeah, we know that 0, 1 is in the critical region, and also from tables, we know that the probability that we get that Y is bigger than or equal to 10, so that was, what was that? That was 0.048, which again is bigger than 2.5%. So 10 is not in our critical region, but we also found out that 11 was in our critical region because the chance we got 11 or more successes was 0.0171, which is now less than our significance level in the lower tail. So therefore, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 is in our critical region. So our critical region is going to be 0, 1, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if we collect our data, so our sample of 20, And if we get those numbers of successes, we reject H0. Now, what did we get from our data? We got 3 successes. So is 3 in our critical region? No, it's not in our critical region. So therefore, because 3 is not in the critical region, we would have to accept H0. So obviously we get, the same conclusion as before. It'd be a bit worrying if we got a different conclusion, but we get the same conclusion as we wanted. I'm just going to try my best to move all my writing up. This may fail because I've got so much writing on the screen. I know it's failed again. Right, let me do this. Let's see if this works. Right, now let's move everything. Oh, this is going to be really tricky. Right, there we go. That's my best attempt at doing that. I'm going to move this over there as well. Okay, so therefore we can say, 3 successes is not in critical region. So therefore we want to accept H0. So again, accept H0 because it's not in the critical region. So 3 is not in this critical region. So we accept H0. Now, again, obviously you want to write down this same conclusion again. So insufficient evidence to suggest that the probability has changed. So the probability of picking someone with a height less than 159.9 centimeters. I know my writing is quite small, but you just want to write that same conclusion out again. So you write out your same conclusion. Make sure you don't forget to write that conclusion, because obviously you're going to lose a mark if you don't write that conclusion in context of the question. So those are the 2 methods you can use. You can use a probability value method or this critical value method, where you get the critical region and then you say, okay, when you collect your data, is the number of successes you got in your critical region? If it is, reject. If it's not, accept H0. And I know I said about AQA students as well who don't get given these tables. So what you would do if you're an AQA student is you would do what we did here. So you work out, so exactly what we did here. So the probability that y is less than or equal to 1. Now you can use your your binomial CD to work this out. So you just want to use your binomial CD. So you don't have to worry about using these tables. You just want to go to binomial CD. Your X is going to be 1. Your P value 0.3. Number of trials is going to be 20. And then you'll get this value that we got here. So you'll get this 0.00676. You'll get that value there. And then what you want to do is you want to do the same with the probability that y is less than or equal to 2. Again, this is binomial CD, but now your X is going to be 2. Your P is going to be, again, 0.3. Your N is going to be 20. And then when you do that, you'll get a number which is bigger than 2.5%. So you know that X equals 1 is your critical value. So you know that 0 and 1 is in your critical region. And then you want to do the same calculation that we did before. So again, you want to calculate the probability that y is bigger than or equal to 10. And remember, that's just going to be, so this probability there, so remember, probability that y is bigger than or equal to 10 is equal to 1 minus the probability that y is less than or equal to 9. Because remember, we're dealing with discrete data. And again, you can use your binomial CD to work out this probability and then do 1 minus that. And then you do the same calculations we did here with the probability that y is greater than or equal to 11. And even if you're an Edexcel student, you can use your binomial CD as well to get your critical region too. So you can do that as well. Okay, so that'd be that question done there. Hopefully that all makes sense. But let's go to the next part of the question then. So part C, determine the actual significance level of the test. So this is the thing. So when you're doing a discrete data hypothesis test, your significance level is not exactly 5%. So the probability that you reject H0 is not actually 5%, because we're dealing with discrete data. And because we're dealing with discrete data, what that means, I mean, if I try and draw like a chart to illustrate this, so I'll do question number C. So, I mean, this is just like some random chart. I mean, let's just say we've got another experiment. So let's just forget our experiment for a second. Let's just say you've got, let's just say you're going to flip a coin like 8 times, okay? Flip a coin 8 times. So your x-axis is your number of successes. So 5, 6, 7, 8. So number of successes is your x-axis. And your y-axis is going to be the probability of that, the probability. So let's just say, I don't know, let's just say that this here is, well, let's just draw like a random line chart. Random line chart like this. And let's just say, I don't know, let's just call this 0.1. Let's call this 0.15. Let's call this 0.2. I'm probably going to go too high, aren't I? Let's just call this again 0.2. 0.1 plus 0.15 plus 0.2 plus 0.2. Let's just call this 0.15 again, so plus 0.15. Let's call this 0.05, so plus 0.05. So we're at 85% so far. Let's call this 0.05 again. I know the heights don't match, but just bear with me. And let's call this 0.0. Again, I know the heights don't match. Let's just call this 0.06, and let's just call this 0.04. Okay, right. So all these probabilities there add up to 1 when you add them all up. Now, let's say you're doing a hypothesis test with this data here. So you've got your upper tail there of your significance level. So I'll call this UT for upper tail. And you got your lower tail, like somewhere down here, your lower tail. Now, obviously, if you're doing a 5% hypothesis test, well, it's impossible to do that because obviously you've got a 10% chance of getting 0 successes. So the significance level of a discrete distribution will not exactly be the significance level that they give in the question, because with discrete data, your probabilities are not exactly going to add up to, you know, the number that you want. So let's say you're doing, for example, right, let's say you're going to do a 5% upper tail, one-tailed hypothesis test. So you've got a 4% chance of getting you've got a 4% chance there of getting 8 successes, haven't you? So you've got a 4% chance of getting 8 successes, right? So if you're doing a 5% significance level one-tailed test in the upper side of the distribution, right? We know that 8 would be in the critical region because 4% is less than 5%, right? But 7, would 7 be in our critical region? So remember the probability that this, so let's just call this distribution here X. So the probability that X is bigger than or equal to 7, we can see from our distribution here that that would be 0.06 plus 0.04. So that's going to be 10%, right? So that's bigger than 5%. So let's just say this is a 5% significance level test. This probability of getting 7 or more is bigger than 10%. So 7's not in our critical region, but 8 would be in our critical region. Now now we said it that we're doing a 5% test, but the probability that we get 8 successes is 4%. So the probability that we reject H0 is actually 4%, not 5%. So the quote actual significance level of this test here, this random thing that I've come up with here, is 4%, not 5%. Do you get what I mean? So even though, right, we were doing a 5% test in the previous part of this question, it doesn't mean that the genuine significance level of this test is 5%, because we're not dealing with like continuous data, which is like, you know, continuous graphs and continuous functions. We're dealing with discrete line charts here, which may not exactly add up to 5%. So 4% is not 5%. So you've got a 4% chance of rejecting H0 with this test, but that's not the 5% that we specified. So even though we could be doing a 5% test, doesn't mean that your genuine significance level for your binomial distribution is 5%. Doesn't mean the chance you reject H0 is genuinely 5%. So that's what this question is all about. So I'm going to go to the next page to do this question properly. Okay, so we can actually use what we did before to help us out with this one. So I know that, again, my writing is really small here because I've obviously zoomed everything in. But what we can see from our critical value test, so what we did back here, this work back here, is that the probability, so that we know that our critical region was this here. So let's write down our critical region. So if you did your hypothesis test and you used this p-value test, what I'd recommend to do for this part C is to get the critical region. So to get these numbers in the critical region. So for part C of the question, we're going to say this. So we know that our critical region, is this here. So so x equals 0, 1, and then 11, 12, 13, ... all the way up to 20. So again, that's our critical region for this test. Okay, so now we've got two parts of this critical region. Remember, we've got the lower part, so the lower tail, and we've got these numbers here, which are in our upper tail of our critical region. So I'm just going to split this into two. So in our lower tail, so LT standing for lower tail. So in our lower tail, right, the probability that we got less than or equal, sorry, I've used y instead of x, haven't I? So again, if we go back to what I've done here, I've used y, the letter y instead of x. So the probability that we got one or less success, that was the number that we got here, wasn't it? So this was this 0.0076. So again, we can use the binomial CD function to work that out, or we can use our tables. So this was 0.0076. And remember, the probability that we got two successes, again, we can use binomial CD to work this out, or we can use the tables. So the probability that we got two successes, again, I'll just use my binomial CD to work this out just now. So binomial CD, x equals 2, p 0.3, and n trials is 20 trials for this test. If I just work this out again using my tables, just because I've got my calculator. Sorry, I use my calculator because I've got my calculator in my hand. Binomial CD, two successes. Yeah, so you'll get this. So 0.035, 5 to 3 significant figures. Okay, right. So remember, two-tail test. So the question, so forget like my explanation here. We're going back to this real question where we got this two-tail test, 2.5% in the lower end, 2.5% in the upper end. That's what we're doing. So remember that basically 2 is not in our critical region, but 1 and 0 are in our critical region. So the probability that we reject H0, so the probability, yeah, so the significance level in the lower tail is actually this number here. So the real probability that we reject H0 in the lower tail is not 2.5%. So I know we dedicated 2.5% of our significance level to the lower tail, but that doesn't mean that's the real significance level for this binomial distribution. The real significance level is this. So remember this, so getting two successes, the probability of getting two successes is bigger than 2.5%. So this is, you know, this 2 again is not in our critical region. 1 is, so the probability, so probability, sorry, I've not spelled probability right. So probability of rejecting H0 in lower tail is actually not 2.5%. So not that 2.5% chance that we did the test based on, right? It's actually this 0.0076, right? That's the chance we reject H0 in the lower tail. And that's what significance level means. So significance level, the definition means the probability of rejecting H0, given that H0 is true. That's what the significance level is. So the chance we reject H0 in the lower tail is 0.76%. In the upper tail of the distribution, so again, we're going to use what we had before back here. So the probability, so this data here, let me just put like a red box around this here. So again, you can use your binomial CD to work this out, but we're just going to copy those data there. So the probability that you got 10 or more successes in the upper tail, so 10 or more successes, what was that number again? It was 0.04, so 0.0048. And again, this is bigger than the 2.5% that we're dedicating to the upper tail. And then we worked out this probability of getting 11 successes. So that was 0.01. I think it was like 71, wasn't it? Yeah. So 0.071, which is less than 2.5%. Okay, so again, what we're just basically copying out again for this part C of the question is just, reinforcing the idea that 10 is not in the critical region, but 11, 12, 13, and so on are. So what is the real significance level in the upper side of the distribution? So again, what is the probability that we reject H0 in the upper side of the distribution? It's this number there, isn't it? So again, the probability we reject H0 on the lower side was actually this number. And the probability we reject H0 in the upper tail is actually this number here, this 0. I forgot the point again there, 0.0171. So again, probability of rejecting H0 in the upper tail is not 2.5%, even though we're doing a 2.5%, we're dedicating 2.5% to the upper tail, it's actually 0.0171. So what is the actual significance level for this test, the real significance level for this hypothesis test? Well, it's just going to be adding those two probabilities together. So the probability of rejecting H0 in the upper tail plus the probability of rejecting H0 in the lower tail. So the real significance level, so the actual sig level is actually 0.0076 and then plus 0.0171. Okay, so 0.0076 in my calculator plus 0.0171 is 0.0247, which is equal to 2.47%. So the actual significance level for this test is not 5%. So we're doing a 5% two-tail test. But in reality, using this real binomial distribution, the chance you reject H0 is actually 2.47%. So we were doing a test where we decided, as statisticians, we decided to ourselves that we're going to do this 5% test where we've got a 5% chance of rejecting H0. Well, actually using the real distribution, the chance of actually rejecting H0 is actually 2.47%. So that would be the final answer to part C. Okay, great. So we're nearly there. Very well. I mean, this could be a kind of exam question. I know I've taken a long time to do this, but I just want to make sure you guys understand everything that we do. Now, part D of the question. So the student with the lowest height in next year's year 13 cohort. So out of, you guys have now finished, you graduated year 13, next year's year 13 students. So the lowest person has a height of 145 centimeters. With aid of a calculation, justify whether the normal distribution model we used in this question would be appropriate for the heights of the group of the next group of year 13 students. Okay, so let's think about this. So the lowest height, so for part D of this question, have a little think about this one. So we know that the lowest height in next year's year 13, so lowest height is equal to 145 centimeters. Okay, so that was our lowest height. So now if we go back to again back to the question, so the lowest height in this set of year 13 students is 145 centimeters. So what I'm going to do is I'm going to define a distribution. Let's just call it H for height. So the height of these year 13 students, we're going to assume is a normal distribution, and the same distribution we had before. So it was 65 centimeters mean, and your standard deviation was 14.5. So your variance was 14.5 squared. So that was just what we did in the question before. Okay, so again, if we read the question we had before, we've got the same distribution. So next year's year 13 students, we assume have the same distribution as last year's year 13 students. So that's what we're assuming. So basically, right, if the lowest height in your year group is 145 centimeters, well, it means the probability of picking someone with height less than, so the probability that you pick a height less than 145 centimeters must be 0. Because obviously, the lowest person, so think about your year group, right? Person with the lowest height is a height of 145 centimeters. Well, the chance you pick someone in your year group who's got a height less than that must be 0. So this equals 0. So what we want to do is we want to use our normal distribution assumption. So this like H distribution here. And again, this H here, so H is the height of a randomly chosen, so height of randomly chosen next year's year 13 student, but I just say year 13 student just to make my writing not as long. So probability of picking someone with a height less than 145 centimeters should be 0. But let's now calculate using the normal distribution what that is. So if we assume that this normal distribution is true, what does the normal distribution tell us? What's the probability that we pick a height less than 145 centimeters using our normal distribution? So remember, we're calculating an area. So do a little sketch again. We've got a normal distribution, 165, 145, somewhere there. What is this area under the curve here? So remember, we're accumulating area. This is normal CD. So your lower is just going to be something massive and negative. So let's just say minus 10 to the power 10, just a really massive negative number. Your upper value is going to be 145. Your sigma is going to be the sigma 14.5. Your mu is going to be 165. Now let's plug that onto the calculator. Let's see what probability that we get. Normal distribution, normal CD, lower minus 10 to the power 10, for example, which is a massive negative number. Upper 145, sigma 14.5, mu 165. So we get a probability about 8%. So 0.0839 to 3 significant figures. Okay, so we got about an 8% chance of selecting someone with this normal distribution with a height less than 145 centimeters. So is this suitable? So you can basically make a conclusion, and you can say, well, so this is about, it's about 8.39% chance. So what you'd say is we have, so assuming the normal distribution, assuming this normal distribution. So assuming this normal distribution, we have an 8.39% chance of selecting someone with a height less than 145 centimeters. Again, I'm just going to make my writing smaller. So less than 145 centimeters. But we want this to be as close to 0 as possible, because there's no one in our year group who's got a height less than 145 centimeters. But we need this probability to be close to 0. To be close to 0. So therefore, what you can say is, you can say, well, maybe this normal distribution is not appropriate. So therefore, this normal distribution may not be appropriate. So a normal distribution may be appropriate for the heights of these students, but maybe the variance is too big. Maybe the standard deviation is too big. So therefore, this normal distribution doesn't look appropriate. Doesn't look appropriate. Doesn't look appropriate. And then you could say, if you want to, looks like the standard deviation is too big. So it looks like standard deviation. So I'll just call this SD is too big. So it looks like the spread of this distribution is too big, because basically the area under there is about 8.4%, right? And it should be as close to 0 as possible. So yeah, I mean, it looks to me like, it's a bit too. So this assumption, this normal distribution assumption, looks like it's a bit too spread out, because we want it to be as close to 0 as possible, but we got about 8.4%. So it looks like the standard deviation is too big. So just some kind of conclusion like that would be fine for a question like that. So no, very long video today, but hopefully that was helpful, because that question that I came up with goes through quite a lot of areas, quite a lot of techniques and topics. So hopefully that was useful. But any questions, do drop them in the comments below. And if you're watching this on the 19th of June 2023, it's the day before your paper 3 exam. So good luck, and I wish you all the best of that. So hopefully this video today helps. So thanks a lot for watching. Please do subscribe and comment and like the video.